Hello everybody, welcome to the case study lecture about Wingtra. In this presentation, I want to tell you how we applied the things you have learned and will learn in this lecture practically during the development of the Wingtra drone. First, I want to quickly introduce myself. My name is Sebastian Verling and I am one of the founders of Wingtra, where I'm currently working as a software developer and mainly focusing on embedded software development, such as, for example, the software of the autopilot. Until mid this year, I was also pursuing my PhD at ASL, which I've now finished, where I was mainly focusing on control and estimation for VTOL tail sitters. Okay, now to Wingtra. What is Wingtra? Wingtra is a spin-off company from ETH with the goal of providing an efficient VTOL platform for aerial imaging, precision agriculture, and mapping purposes. It originally started as a student project at ETH back in the last year of my bachelor's studies. Back then, the vision was to create an aerial robot that combines the flexibility of rotary wing systems with the range and efficiency of fixed-wing drones. This would then allow to have a long-range platform without any additional requirements, such as, for example, runways or wide open spaces for takeoff and landing. This enables a wide range of different applications, such as, for example, precision farming, search and rescue, or transportation. Now, one of the more famous platforms that does combine these two properties is the Osprey, which you can see in this picture here. That is also what inspired our design back then in the Focus project. Here you can see a picture of the group or of the team with which I pursued the Focus project, where here you can see me when I was still younger than I am now. Now, on the right side here, you can see a picture of the system that we developed, where you can here in the front see the two propellers that can be tilted forward. In the back here, we have a third propeller that can also be tilted sidewards, such that we can operate it like a tricopter. Here you can see a video of the final prototype hovering. You can see that this is something that we did manage to work quite well here. Now here you can see then a video of our first and last cruise flight we performed with the plane. Please excuse the bad video quality, but this was the only footage that I could find of it. Now, as you could see, it didn't go that good. Unfortunately, this was around 1 week before the end of the project and the rollout of the Focus project. The reason it crashed was most probably because the right wing stalled, as it pitched up too early at takeoff. Now, at the end of the project, we looked at it again and found the following issues with the design of the drone. On one hand, it was too fragile. You saw that it didn't really crash from a high altitude, but still was pretty much completely destroyed. Another disadvantage was that it had 10 actuators. It had 2 here, the propeller and the tilting mechanism, another 2 here for the other side for the propeller and the tilting mechanism, the ailerons here and here, the elevator, the rudder, and here again a propeller with tilting mechanism. Now, even though we had this many actuators, we still didn't have any redundancy. Finally, the manufacturing process was pretty complicated and therefore it couldn't really scale. So if we would want to manufacture multiple of them, it would be pretty expensive. Now, these points were things that Basil Weibel here addressed in the bachelor thesis that he did. He was also the initiator of the whole project to develop this VTOL airplane. Now, in his thesis, he proposed an alternative design with a much lower complexity. It was the tailsitter design that you can see here, with 4 propellers and 4 flaps in the back here that you can unfortunately not see. This allowed much cheaper manufacturing and was much more robust. It is also easier to scale it up, as if you want to have it smaller, you could basically just cut in half here and just have one with 2 propellers and two flaps, but you can also scale it up as much as you want. Now, after we finished the project, which let's say partial success, Basil and me could continue to work on this alternative design, where he was mainly focusing on the hardware and manufacturing part, and I was more focusing on software and electronics. Many people, however, were rather doubtful in the design and weren't sure if this can even fly. So first, we focused on making a proof of concept. For this, we first designed a very simple hover controller, where we assumed that the moments we can create to control the system are generated according to these equations that you can see here. They basically mean the following. The moment we can create around the body x-axis is directly proportional to the differential flap deflections of these two flaps. The reason why this generates a moment is because the slipstream that is created by the propeller is on this side deflected in this direction and on this side deflected in this direction. This creates then a force on the flaps, and with the lever to this axis here creates a torque around the body's x-axis. Similarly, we can also create a pitching moment, a pitch around the body y-axis here with collective flap deflection. Now, in order to create a moment around body z-axis, we just use differential thrust. Now, these are rather simplified assumptions, as for example, we didn't look into how different propeller speed and inflow speed change the efficiency of the flap and the moment generation here. But because we wanted to go simple first, and then we can still increase complexity as the project goes along and we see issues with it. The reason why this is okay is in nominal hovering conditions, it's okay to assume that the overall velocities are rather small and the propellers turn approximately always around the same RPM. Now, in order to tune the controller, we did the following. You can here see me back here, how I was tuning the controller when we put the system into a rig where we only allowed 1 degree of freedom at a time. So here you can see how we then tuned the pitch performance of the controller. Here you can now see a video of how then the whole system came together. You can see that it looks pretty stable. The cable that you can see that goes towards the aircraft is such that we could have an emergency shutdown in case the system would do something unexpected. You can now see how we tried to fly a rectangle to see how we can actuate in all the important directions for moving the system. Now, after hovering, we wanted to also show that cruise works. The problem with cruise, however, is that we couldn't really tune a controller before that, and we couldn't by far do a transition from hover to cruise flight. So there we had to think on how we want to solve this problem. This is what you will see then in the second part of this video. In the end, we ended up mounting skis on the system and went to an empty cross-country skiing slope where we could then try to fly it in complete manual mode. So this was completely manual flown by a pilot without any interaction of the controller, just to see if we can make it fly. We then had to do some trimming because there was no controller at all. And then you can see finally that it was flying pretty stably. Then after doing some turns and see how it reacts to different inputs, we then again started to descend and finally approached for the landing approach. As you can see now, he was pretty relieved that everything went well. Okay, so after we had this proof of concept, we then saw its potential and wanted to make a company out of it. For this, we also then had team growing, where we then also had Max and Elias joining our team. And they already had some experience in developing a business, as they are still the owners of Kleine Freiheit, this small cafe down at Haldeneck. Max, the tall guy here, he was also studying mechanical engineering in the time, and Elias was studying economics and business. Now, in the meantime, we then also scaled down the system from this originally 2.4 meter span system to this 1.6 meter span, because it was just easier for testing purposes. Okay, so now that we had the proof of concept done, that we can basically fly in, hover, and cruise, it was now about getting the system to run in all its operating modes, which means we have to design a controller that can make it hover, that is also able to transition from hover to cruise flight, that can also then, of course, cruise, and then also do the back transition from cruise flight to hover flight, and finally land again. Now, there are some controller designs out there that do fulfill these requirements, but they have some discrete switching between hovering and cruise flight. But this is something we want to avoid. We wanted to have a controller that can cope with all of these different dynamics. Now, first of all, we then needed to have a model for cruise, because you already saw we have some simple model for hover, but for cruise we didn't have anything. Now, for this, we used the following tools. For the simulation of the thrust and the slipstream behind the propeller, we used QProp, which is an open source tool that you can use for simulating propeller dynamics. For the aerodynamics of the main airfoil, we then used XFLR, which allowed us to generate these lift curves that you can see here. We also did then the same thing for drag and the moment coefficients. Now, the problem though was that this XFLR tool only gives us data before the stall point. But because we might have a way bigger range of different angle of attacks, we also needed to know what happens afterwards. So basically after the stall point here. For this, we were using historical wind tunnel data of an airfoil that has a pretty similar shape as the one that we use. After then having basically knowing the thrust, lift, drag, and moment through these equations here, we then tried to create a model out of this and tune a controller for that, which didn't turn out that well, as you can see in this picture here with like everything being bent. So we did need to have a better model because the simulations didn't quite capture all the effects correctly. In that time, we also already saw the first advantage of kind of downscaling the system to this one here. And we then even downscaled it further because it just made everything much easier. So we then ended up with these two here that had a span of 1 meter and also reduced number of actuators. So you can see that these now only have 2 propellers and 2 flaps. The original idea why we wanted to have 4 is because of redundancy. In case one propeller would fail, we would still have 3 left, which we could use for controlling the system. But at this point, we saw that maybe we should first making it work at all before focusing on redundancy. So this is why we then scaled it down. Now, in order to get better data for the model, we then went to a wind tunnel, because there we thought we can address the weaknesses that we have in the simulation, which were mainly the problem with the propeller wing interaction and the slipstream behind the propeller. So basically, how does the propeller slipstream influence lift, drag, and the moment that we can create with the system, but also generate all the high angle of attack effects. So for this, we went then into the wind tunnel and measured with this rig here. You can here see maybe that there's a force torque sensor where we measured all the forces and torques that were acting on the system for different inflow speeds, RPM of the propellers, angle of attacks, and flap deflections. Okay, so after having this data, we could then continue. Now here you can also see some images of the wind tunnel in case you have never seen one. This is the wind tunnel at IMPA that we could use. So then one simplification that we did to make everything a bit less complicated is that we assumed for now that the angle of attack always corresponds to the nominal angle of attack of 5 degrees. We said that this is good enough for regular operations, and it did allow to reduce the complexity quite a lot. So having then the data and this assumption of a constant angle of attack, we could then use this model here. Now it's worth noting here that this is a model that is only an approximation, which is very close to the Taylor series expansion of an actual more complicated model. So the reason why I'm saying this is a formula that you will not find on any of the other fixed wing lecture slides, because this is just a simplification. Now, with this polynomial model, we then could not only have a kind of low complexity model that tells us, with given the conditions, what forces and moment act upon it, but we could also easily invert it. So we can now use this model for both simulation, but also for the control allocation. Okay, so then after having this new model, we then also needed to design a better controller, because the previous one was could only handle hover. Now, the design choices that we made for this new controller were that it shouldn't do any switching, as I mentioned before, but it also cannot have any singularities. So we cannot use Euler angles, for example, that have a singularity at 90 degrees pitch if you use the 3:1 Euler angles. We also wanted to have an easy integration with high-level controllers, and very importantly, it has to be computationally lightweight, as it's running on a small microcontroller. Now, the controller itself, that basically tells us what moments we want to apply given the current attitude and the rates and the preferred ones. The equations for this are written out here, where R, the uppercase R, is the rotation matrix of the current attitude, and RF is the rotation matrix of the desired attitude. EZ is here just the unity vector in Z direction. The omega here are depicting the angular rates and the angular rate reference respectively. So we then can say that the moment we want to apply to the system is some gain matrix times the attitude error and a gain matrix times the angular rate error. This part here in the end is just to compensate for some rigid body dynamics. Now having the controller and also now the control allocation, which we based on the previously seen wind tunnel data, we could then tune the controller a bit, and this is the result after some initial tuning, where you can see the pitch angle tracking during the forward transition and the backward transition. So here in red, you can see the pitch angle reference, and in blue, the actual angle. Same for here from hover to cruise flight. We can see that this tracking works pretty well, but we can also see that here you can see that it looks like there is some slight delay or not, the tracking is not very optimal. This is most probably due to the effects that we neglected for higher angle of attacks, because we always assumed that it will be 5 degrees. And if you imagine at the forward transition, when you go from cruise to hover flight, that the angle of attack will probably not always be your nominal 5 degrees. But we could see that it did work out in the end. So now after having kind of this proof of concept of the controller, where we can control it in any regime, we then were finally ready to make a promotional video and start looking for funding. So this was our very first promotional video. Yeah, so that was our first video. So now that we had a system where we could show that we can hover, we can transition, and we can cruise, we also needed to have something that is usable, right? So the problem with the design that we had before, it was just a plank and it couldn't carry anything. Now for real applications, we also need to have a payload, may it be parcels for transportation or cameras for aerial imagery. So that's why we then went for a design iteration where we added this payload belly that you can see here. And then also after kind of having the flight controller ready, it was also about kind of making it easy to use. So also adding more higher level control algorithms and planning. Now you could see here that this design here that we did was quite bulky and wasn't really aerodynamically efficient. So we quickly after introducing this one also optimized the aerodynamics of it and then ended up with this design here, which is roughly the design that we still have now. Okay, so now after making or trying to make it usable, we also have, or on this process of making it usable, we also faced many issues. One of those were related to the size of the wind tunnel, which didn't allow us to record data for angle of attacks higher than 55 degrees. Now, why would that be important? Because we already saw before that it kind of also worked pretty well without that knowledge. The main problem is with flying in high wind conditions, because you have to imagine that if we're hovering and it's very windy, then the wind is actually coming from a very high angle of attack, close to 90 degrees. Now, in this plot here, you can see the pitch tracking if the controller doesn't know that, and we do have these windy situations. Now, here you can only see kind of a plot, but how this can actually look in real life if you let this controller fly in wind is something that you can then see in this video here. You can very clearly see how the performance of the controller degrades a lot if it doesn't know what's happening. So that was wind between 4 and 8 meters per second to kind of get a relation for this. Now, in order to overcome this problem, we first tried to find a way of estimating the wind, because the more you know, the better generally. So a typical approach to estimate uncertain quantities is through means of Kalman filters, which is also what we then did. Now for the propagation step, we assume that the wind in the next time step is the same as it was before, because usually you don't really know how the wind will change in the future. And your best assumption is that it stays constant. Now for the measurement step where we want to correct for it, the question is, what do we put there? Because we don't really have a sensor that tells us the wind speed in hovering conditions. For this, we first looked at the influence the wind has on the system. Now, if we assume that we're in an equilibrium, all forces on the system have to cancel out. Now, looking at all the forces we have the thrust from the propeller, we have the lift and the drag that is induced by the wind, and we have the gravity force. Now, assuming that lift and drag force behaves qualitatively like a flat plate, we can then find this relationship here that can be simplified to the following equation, where we can then say that the free stream velocity is somehow proportional to the square root of the tan of the pitch angle. Now, this was then the free stream velocity, but that's not wind yet. So we also have to account for the ground speed, which we can do through the wind triangle, which you can see in this formula here that relates these three quantities. Now, with this presented approach, we can only estimate the free stream velocity in the body frame. So we also have to first transform it back into the Earth fixed frame. Eventually, we end up with this formula here on the bottom, where we can get all quantities from the sensors and the EKF that is already running on the system. We now only need to get these constants K to tell us how exactly the wind influences it. Now, as we saw, the wind tunnel was too small to do this. So what we then did is the following. Because the wind tunnel was too small, we had to get this data in actual flights. So we went flying on a day without any wind and used constant pitch and roll references and waited until we reached a steady state condition. Then, as there is no wind, the free stream velocity is the same as the ground velocity. I hope the video isn't as flickering for you as it is now for me. But I hope you can see what approximately we did. So after then doing this for multiple different pitch and roll angles, we ended up with the following data points in blue and our fitted model in red, with the standard deviation with the shaded red. Now, if we now use this information, we can then try to estimate the wind as we proposed before. And here you can see the results of this. Now, in blue, you can see the estimated wind magnitude on the top and direction on the bottom. And in red, you can see the measurements that we got through a wind sensor that we mounted on the ground. Now, it only sampled once every second, so that's why you only have this or once every 10 seconds, that's why you have this very crude resolution of it. You can also see this range here, which gives us the standard deviation of the measurement of the sensor. Now with this blue dashed line, you can see the yaw angle of the system. So basically in which direction it was facing, because we want to show that even when we change it, both magnitude and direction of the wind estimate stay constant, or not constant, but don't change as much. And we could show that it didn't have any influence. Now, using a similar approach to also get rid of the moment offsets that we need in the controller to kind of get a better pitch controller performance, we could then kind of get, with the similar approach, this data here in blue and use the polynomial fit in red to know how much the controller has to compensate for it. Here you can then see the improved controller tracking on the bottom compared to how it was before on the top here. We can see that there is still some offset sometimes here, but that's something that we can easily get rid when we add an integrator to the controller. It's just about getting the first initial guess right. So after applying these methods, we went then testing in a lot of wind, and here you can see the results. You can here see that the wind almost loaded away, but it could still recover and then stably hover in position. We then also try to kind of move forward and backward to see that we still have all the degrees of freedom that we want to have. And you can see with these heavy winds, it almost looks like it's cruising. Especially when moving forward. Okay, so when analyzing the data, we found one additional nice thing. So here we can see the power consumption here for the first hover, then for cruise, and then for the second hover for landing. And we can see that in the no wind case, the power consumption in hover for landing, for example, is approximately 3 times bigger than the one in cruise flight if there is no wind. Now, if there is wind, we could see that we could drastically reduce the power consumption during hover. The reason for this is the heavy wind, if you think this is now the drone, also when coming from this side, produces quite a lot of lift in addition upwards. So we don't have to use as much thrust to produce the lift because actually the wind helps us in staying airborne. This is why we could then at around 8 meters per second wind reduce the power consumption hover by a factor of almost 3. Now, one additional problem that we sometimes had in wind is that it was tipping over if it just shuts down the motor when it hits the ground, which is what you can see in the left image here, or in the left video here. But if we just cut off the motors slightly before it touches the ground by using, for example, a distance measurement, it can greatly improve this, that it will not tip over. Now, one further issue that we did see is the following. When doing the transition from cruise to hover, we can see that there's a substantial gain in altitude. As the descending speed of the system is limited, this will also lead to more time for landing and therefore increased power consumption. And that means that we in total will have less flight time for the drone. Now, this is something that we want to optimize. The way we did it is through a model-based optimization, where we have an optimizer that gives us the optimized values for the pitch set point and the thrust that we feed to the controller. Now, the cost function that we want to minimize is the following. The first term here is there to minimize the change in altitude. The second two parts here are to guide the system in the right direction of actually doing a transition. So the first term of these two is minimizing the total velocity to 0, and the last one is minimizing the difference between the current pitch angle and the desired final pitch angle after the transition. Now, in order to run this optimization, we need to have a way better model. This we created through the following formulas that you can see here. Now, these won't be too important for you now. I just have them here so that you can see them. So on this slide, it's basically a summary of all the new formulas that we use for additional forces, or a better calculation of forces to have more accurate representations on which forces do act on the system. In this slide here, you can then see summarized on how we mix the influence of the external inflow with the slipstream of the propeller, as this will then result in a new effective inflow speed as seen from the airfoil and a new effective angle of attack as seen for the airfoil. Now, when using this, then we then have the new drag, lift, and moment formulas, as you can see here. Now, after letting this optimizer run, we end up with the following, where here, in order to robustify the approach further, we added this feedback controller for the altitude. So we do have the pitch set point from the optimizer, the thrust set point from the optimizer, but we also have this additional feedback loop that also adds up to this thrust set points in order to make it more robust if there's slight deviations in the initial setting of the system. Now, when then using this approach, we can see the following results for the transition. In the video here, you can now see the optimized transition where there's a significantly lower change in altitude overall. So in the naive approach that we used before, we had around 20 meters altitude gain, and now it's in the range of 3 meters. The next thing we investigated was about actuator failures, which ones can happen and what we can do about it. Specifically, we have looked at aileron failures, which we looked at for hover and cruise flight. We then also looked at a motor failure. For this failure, we only considered cruise flight, as one motor would not be able to deliver enough thrust to stay airborne. The nominal actuation in hover can be seen in this table. In case of an aileron failure, we lose the ability of differentially deflecting the ailerons. The effects of that are twofold. On one hand, it generates a disturbance if it's not locked at trim, and on the other hand, the resulting system will be underactuated, as we cannot control the moment around body X anymore. Now, as the moment around body X in hover is not influencing the stability of the system, but only its heading, basically where it's looking at, we can give up control around that axis. Now, when accounting for this in the controller, we do get the following result. As these are rather dangerous tests, we were using this small foamy plane here to see how our algorithm works. Here we can see a video that shows us how the system reacts to this failure. In the bottom, you can see the roll and pitch angle tracking, as well as the actuator commands. At first, there wasn't any failure yet. We then locked the right aileron at trim angle. In this failure mode, the attitude references are given by a pilot, and we can see we can still guarantee the stability for both the roll and the pitch axis. In the next failure case here, we lock the aileron at an angle of 15 degrees away from the trim angle. This results in a constant disturbance around body X. This time the attitude references are given by a higher level position controller. And we can see that we did lose the control over the heading, but we were still able to track the position of the system. Now for cruise, the situation is very similar, except for the fact that the axis around body Z is passively stable through the vertical fin of the system. Again, the locking will result in a constant disturbance in case if it is not locked at trim. Here, however, we do have the possibility to change the control allocation to use differential thrust to control the moment around body X. This is also important as in cruise, the X-axis does influence the stability of the system. The way differential thrust creates a moment around body X comes in three parts. As a first effect, the increased thrust on one side also increases the drag of that propeller, which induces a moment. Secondly, the increased thrust also creates increased slipstream and therefore more lift on that side. Lastly, due to side slip and the sweep of the wing, also this wing area here is more directly affected by the incoming free stream velocity and therefore creates also more lift on that side. Now we then included all of these effects in the control allocation, and here we can see the results. Overall, the performance is similar as in the nominal case. Now it is important to note that with differential thrust, we can only compensate for a loss of aileron to some extent, as the total achievable correction moment is smaller than with two working ailerons, which limits the controllability in cases where we have a locked aileron different from the trim angle. In this case here, we locked it at the trim angle. Finally, we looked at propeller loss in cruise flight. Here we have to note that the passively stable statement is only true to some extent. It only holds as long as the restoring yaw moment from the fin is larger than the moment introduced by the differential thrust. Now, in order to model this effect, we can say that the yaw moment is proportional to the airspeed squared. Therefore, the airspeed has to stay above a critical value, which you can formulate as a function of the differential thrust. Now here the blue circles correspond to the critical airspeed given differential thrust, which we measured experimentally. We then fitted the red dashed function to it, but in order to have some safety margin, we decided to go for the solid red line as our airspeed reference. Finally, here we can see the result of the controller in case of a motor failure. We can see that the attitude tracking is getting worse, but still stays within reasonable bounds. So we can still control the system, as you could see in this video.
Well, that was it for the case study. I hope you enjoyed it. And in case you're interested, you can also find more information on our website under wingtra.com, where we also have open positions in case you're interested. In case you have any questions to the content I presented, I'm also happy to answer them on the 8th of December during the regular lecture time. Until then, I hope you stay healthy and all the best. Bye.